There. Okay, they are on. Okay, my name's Stuart Batten. It's my pleasure to chair this session. So today's speaker is Professor Vanessa Peterson. Vanessa did her PhD at University of Technology, Sydney, and ANSTO. And that following that were research positions at UTS, University of Maryland, and particularly with NIST, and the University of Sydney. And then following that, she joined or rejoined ANSTO, where she's now a principal research and neutron instrument scientist. And then in 2016, she was also appointed as an honorary professorial fellow at the University of Wollongong. And today she's going to talk to us about neutron and X-ray diffraction of functional materials. Vanessa.
Thanks, Stuart. Not just diffraction. Okay, so thank you to the organisers for inviting me here. It's my great pleasure to talk about in situ and real-time analysis of functional materials. It's my first time in India, so I'm very, very happy to be here. Okay, so I work at ANSTO, which is the Australian National Lab of Facility Research, basically. And ANSTO operates the Australian synchrotron, which is in Melbourne, where, incidentally, the IUCR 2023 Congress will be. And I also work at the Australian Centre for Neutron Scattering, which until recently was called the Bragg Institute. And that's about 30 kilometres south of where central Sydney is. And that's shown here, where we have a 20 megawatt research reactor. Now, I did my PhD also using the facilities at Lucas Heights campus, which we're looking at here. And I did my PhD using the old reactor, the high flux Australian reactor, which is only 100 metres away from this new reactor. And it used to take about a week for me to collect a single powder diffraction pattern. And now on the new facilities and the instrument that I spend most of my time on, Wombat, the high intensity neutron powder diffractometer, it takes a few seconds to collect those same quality data. So it's really been a revolutionary time in neutron powder diffraction. And so you can see the natural opportunity for in situ and real-time analysis was right there. Now, I know that Wombat isn't, firstly, it's not an acronym. Wombat is an animal, and all of our instruments are called after Australian animals, except for the Taiwanese instrument, which is called after a Taiwanese animal. And wombats aren't particularly well known for their speed. But in reality, they can run faster than Usain Bolt. So that's about 40 kilometres an hour, which is pretty quick. So yeah, Wombat, you know, it's pretty quick. So Wombat has an area detector. It was built at Brookhaven National Labs, and it's 120 degrees angular coverage, and it's 200 millimetres high. So we can also do, apart from powder diffraction, single crystal analysis, texture, everything in between single crystal and powder work. And as Stuart said, I also hold a position with the University of Wollongong. And the University of Wollongong and some of our other collaborators have really invested in research using Wombat and some of our other instrumentation to look at functional materials. And so I lead a research group from within ANSTO, from within the Neutron Scattering Centre, to do just this. And this is a fantastic opportunity because you have experts who know neutron scattering, but they also know something about the materials that they're applying neutron scattering to. And so therefore, the characterization that they're doing can be tailored to get more quality, higher quality information about a particular material. And this is a very effective model for doing research that's led out of facilities. And we're certainly not the only facility in the world that does this. So within this project, we have a number of past and present postdoctoral researchers, and for the most part, they're at least 50% funded externally by our collaborators. And we work in a range of material areas, but the two major areas that we have invested research in are battery materials and functional framework materials. And we have a computational effort as well, and so we have a cluster dedicated for use by this project. Okay, so the postdoctoral researchers here that you see are underlined. It's their work that I'll be presenting today. And the logos for our collaborators down the bottom are also, that's the work that I'll be presenting. So our role in this collaboration, unsurprisingly, is characterization. And it's important to realize that the characterization that we do, and that ideally should be done on any material, isn't just about obtaining data. It's about obtaining information and insight into what the material is and how, in this case, it functions. And that's a very important distinction. So I'll start with talking about battery materials. And electrodes really are the functional, the performance bottleneck of battery function. So we look mostly at alkali-ion batteries, lithium-ion batteries, and emerging sodium-ion battery materials. And we start with looking at simply the phase composition and the average structure of the electrode powder. We do a lot of other characterization as well, but that's just a first starting point for us. And then we go on and look at trying to understand how the electrodes function within the battery. So at the heart of a battery are two electrodes, positive and a negative electrode. And as you use the battery and draw a current, charge balancing ions are mobilized from one electrode, move into the electrolyte across the separator, and are accommodated by the other electrode. And of course, this is reversible. And so during charging of the battery, this process is reversed. So the aim of the characterization that we do is to understand how that happens. Where are these charge balancing ions? How are they interacting with the host electrode material? And how do they move through that electrode in order to leave the material? And we correlate that information with important battery properties, things like capacity, which is how many charge balancing ions that the material can hold, the rate capability, how quickly those ions diffuse through the material, and cycle life, how many times you can do that reversibly before your battery stops functioning or loses capacity. Okay, ideally we would be obtaining this information during function. So when battery materials first started being looked at by researchers, and I should point out that the first lithium-ion battery was commercialized by Sony Corp in 1991, which is not that long ago. Researchers, to understand function, initially they just look at the electrode powders synthesized with a known amount of lithium within the material. And then later on, you create a battery and charge that battery to a particular state of charge, extract the electrode material and look at that. And then again later on, researchers moved to in situ studies of equilibrium systems. So looking at an electrode material within a battery that's equilibrated at a particular state of charge, and then sequentially changing that state of charge and looking at it again to build up a picture of function. And that's very, very different to looking at an electrode within a battery during charge, because the equilibrium system is not the same as the non-equilibrium system, and that's especially true for battery materials. So electrodes are very fascinating materials, even from a fundamental standpoint. So they accommodate a change in composition in charge balancing ion concentration over a very wide range. And this concentration range continuously changes during the electrode use. And so inherently there has to be points at that composition where there are too few or too many ions to form a conventional crystal structure. Even if you look at the most commonly used electrode material that we have today, graphite, and every electronic device will have a graphite negative electrode in the room. If you look at how that material accommodates lithium, so during lithiation on charge, you have ions that insert between these graphene sheets. And if you look at the corresponding OL reflection from that stacking axis, and this is neutron powder diffraction data at quite a long wavelength here from Wombat, you can see that there are characteristic changes in that correspond to structures that form during that process. And traditionally and conventionally, these have been treated as discrete points in that composition change as average structures. But if you look a little bit in more detail, you can see signatures in the operando data. So if you follow the whole compositional change, and this is data collected on a minute time scale, you can see that there are clear signatures where this doesn't happen. And this not only happens in the OOL reflection, but also within the graphene sheet. So the 100 reflection also shows this. Now, I'm not saying that you can get information on these unconventional structures from this data, but importantly, you can use this approach to identify compositions where they form. And this is very important because you can then go away and use more appropriate tools to understand in detail those structures and how they relate to battery function. So you really need operando methods, and you really need to also look closely at your operando data to see if the structural average is sufficient. So I'm not going to talk anything about unconventional structures any further. I'm just going to look at the average structure from here on in. And of course, we use powder diffraction. And neutrons are absolutely essential for looking at electrode materials. The nuclear scattering mechanism gives rise to an amplitude, a scattering length that varies isotopically. And so that means you often have excellent contrast between elements that are near neighbour on the periodic table. Things like your transition metal elements that are so critical to battery electrode function, iron and manganese being a very, very good example of this. So the first example of an electrode material that we studied to look at function, I'll go through, is this sodium-ion battery material. It's a positive electrode for emerging sodium-ion batteries. And this material has an excellent discharge capacity and good energy density, but it suffers from poor cycling performance. This is an extremely common issue with battery electrodes. It's probably the most common problem with them, is that you get capacity decay after continued use. And we want to see how this arises. And so during that sodiation of this material, that changing sodium-ion composition, you have structural changes that accompany that. And this was well known, obviously, before we went and studied it. But the order in which they appear during that process wasn't clear. And the aim of our research was to look at the phase evolution, really, and correlate this with cycling performance. It's pretty straightforward. So we started off looking at the average structure, and we used data, powder diffraction data, with X-rays and neutrons, high-resolution neutron powder diffraction in this case, so from Wombat. And what we do, and this is a very, very common approach that we take, is to do a refinement against both histograms. And the reason that we do that, even though the critical information on the transition metal ordering comes from the neutron powder diffraction data set, is that the solution that describes both data sets is more likely to be unique and therefore correct than the solution that comes from either one of those data sets. And of course, you can weight the histograms within your refinement strategy, and we do that too. So once we obtain the refinement result, the structure, the average structure, we can see very clearly that sodium is accommodated at 2 sites between these transition metal oxygen layers, and that iron and manganese share the same crystallographic site. You'd never get that from, obviously, the X-ray data. We then moved on to look at the material in situ within a battery. And so one of the other ways that an electrode material functions, obviously, is through changes in the oxidation states of the transition metals as those charge balancing ions are incorporated and released from the electrode. So we took that material and we fashioned a coin cell, and we took a modified coin cell, and we took that to the Australian synchrotron and performed in situ X-ray absorption spectroscopy measurements. So this is not in operando, this is in situ of the material within a battery equilibrated at a known state of charge. In this case, as we synthesized it. So we hadn't charged the battery at all. And this was the same battery that we then took over to the powder diffraction beamline and performed operando powder diffraction. So it gives us a really good baseline of what our material is before we look at the operando, powder diffraction, and structural changes. And what we see is we can clearly identify the oxidation states of the iron and manganese, and we can associate those with features in the charge-discharge of the battery, so the curves, the charge-discharge curves that we measured previously. And that is really important information because it tells us from the outset what we have. Now, at the moment, we can't perform this in operando at the Australian synchrotron, but they have a new fantastic detector coming very, very soon, and we will be able to do this. In operando, X-ray absorption spectroscopy is done at other facilities. It's just that we didn't have